Assalamualaikum and selamat sejahtera. In this video, we will discuss DC voltage regulation using DC Dc converters, or also known as DC Dc choppers. There are three types of DC converters, which are buck converters to step down the input DC voltage, boost converters to step up the voltage, and buck boost converters to perform step down and step up functions. Regardless of different functions, each DC converter requires energy storage, which is an inductor, to operate efficiently. Other than to act as energy storage, the inductor also works as a current filter to ensure continuous and ripple-free DC current flows to the DC load. In the next explanation, we will look in detail about the inductor roles in the operation of each DC converter. Lastly, to maintain continuous and ripple-free DC voltage across the load, a capacitor is used as a voltage filter. Typically, the capacitor is connected in parallel to the load. In the next explanation, we will neglect the role of the capacitor while discussing the operation of the DC converters. Later, when we discuss the design procedures of DC converters, we will consider back the role of the capacitor. I will use the water distribution system as an analogy of the operation of DC-DC converters. Based on the diagram, the self-generated utility water tank represents the input DC source of the converter's circuit. Next, the consumer tank represents the DC load, which is a resistor in the circuit. In this system, the water-generated tank can generate water when there is a water flow. This tank acts as water storage of the system. Hence, this tank will represent the inductor because the inductor will store magnetic field when there is a current flow through it. To let the tank to generate and store the water according to the consumer demand, a controllable power switch is used to regulate the operation of the tank. In the DC converter, a transistor such as IGBT, BJT, or MOSFET is used as the controllable power switch. Once the tank stored enough water, the controllable switch must be turned off. When it happens, automatically another switch is turned on to maintain the water flow between the water-generated tank and the consumer tank. This switch cannot be controlled, and it will turn on whenever the controllable switch is turned off. In the DC converter circuit, a diode is used to maintain the connection between the inductor and the resistive load. As a conclusion, other than the capacitor, each DC converter circuit must consist of the input DC supply, resistive load, an inductor, one controllable power switch, and one diode. Now, let's consider the operation of two water distribution systems. In both systems, the utility tanks have 40 meter cubics of water. However, consumer A only needs 30 meter cubic, while consumer B requires 10 meter cubic of water. Based on the consumer's demand, this system will perform a step-down function. Firstly, switch A and B are turned on to allow the water-generated tanks to generate and store water according to the consumer's demand. At this moment, we can see there is a continuous water flow between the utility, water generated, and consumer tanks. Thus, as similar to this condition, when the transistor in the DC converter is turned on, there is a continuous current flow between the DC supply, inductor, and resistor. In this condition, the inductor is energizing to store the magnetic field. Once the water-generated tanks completed their tasks, both switches are turned off. Automatically, the uncontrollable switches are turned on. At this moment, the utility water tanks are disconnected from the consumer's tanks. Hence, the water-generated tanks will act as the water supply to the consumer tanks. Thus, in the operation of the DC converter, the turn-off transistor will disconnect the DC supply from the load, and eventually the inductor will de-energize to supply current to the load. Based on your observation, which switch should be on longer to generate water in the second water tank, where this water reflects the consumer's demand? The answer is A. Due to the demand, the turn-on time of switch A is longer than switch B. Hence, it will affect the duty cycle of the switch, since the turn-on time is directly proportional to the duty cycle of the power switch. Based on these two systems, switch A has a higher duty cycle than switch B. Lastly, let us compare the system diagram with the circuit topology of the DC-DC buck converter. According to the equation, if Vs is constant, hence the output voltage is directly proportional to the duty cycle. Therefore, it verifies the conclusion made in this discussion. Next, we will consider a new topology of water distribution systems. Take note to the new location of both controllable and uncontrollable power switches. As similar to the previous systems, the utility tanks can generate up to 40 meter cubics of water only. Nonetheless, consumer A and B requires a higher volume of water, which are 100 and 70 meter cubics respectively. Thus, this system must perform the step-up function to meet the consumer's demand. When switch A and B are turned on, we can see the water-generated tanks are generating the additional volume of water to accommodate the consumer's demand. At this moment, water will flow between the utility tank to the water-generated tank only. Thus, we can say that these systems are executing the boosting function. Therefore, in the DC converter circuit, the inductor is called the boost inductor. To perform the boost function, the inductor must solely be connected to the DC supply. Hence, the load must be disconnected from the source. Once the water-generated tanks completed their function, switch A and B are turned off and automatically the uncontrollable switches are turned on to connect the consumer tanks to the systems. At this moment, there is a direct water flow between the utility, water generated, and consumer tanks. Thus, in the DC converter circuit, the connection between the DC supply, boost inductor, and resistor is established when the transistor is turned off. Now, based on your observation, which switch should be on longer to generate water in the second water tank? Once again, the answer is A. Because based on the demand, the turn-on time of switch A should be longer than switch B. Eventually, we can see that the duty cycle is directly proportional to the demand. Lastly, let's consider the voltage equation of the boost converter. If Vs is equal to 40 volt and we apply duty cycles of 0.6 and 0.3 respectively, based on the output voltage values, we can verify that the output voltage is directly proportional to the duty cycle as well. Lastly, we will consider another circuit topology of water distribution systems to represent the buck boost converter operation. Once again, take note of the new location of both controllable and uncontrollable power switches. According to the consumer's demand, System A will perform the buck function while System B will execute the boost function. When switch A and B are turned on, we can see there is a direct connection between the utility and water generated tanks only. Hence, this condition is similar to the operation of the boost converters when the transistors are turned on. However, when we look at the water volume generated by the water generated tanks, we can see these systems are using a different approach. Instead of generating an additional volume of water, these water generated tanks have a similar water volume to the consumer tanks. The reason of this condition will be answered when switch A and B are turned off. As you can see, when both switch A and B are turned off, the consumer tanks only connected to the water generated tanks only. The water generated tanks will be the sole water supply to the consumers. That's why the water generated tanks need to generate water equals to the consumer's demand. Based on the connection between the water generated tank to the consumer tanks, it is similar to the connection between the inductor to the resistor in a buck converter operation. However, throughout the system operation, we can see there is no direct connection between the utility tank to the consumer tank. Therefore, In the DC converter circuit, you will see there is no direct connection between the load and the DC supply whenever the transistor is turned on or turned off. Therefore, the converter is also known as the indirect DC-DC converter. However, as similar to the previous converters, the duty cycle is always directly proportional to the demand. To perform the step-down function or buck operation, the duty cycle must be less than 0.5, and to perform the step-up or boost operation, the duty cycle of the converter must be higher than 0.5. I will end this video with the comparison between all DC-DC converters. As we can see, all converter circuits have the same components except the connection of power switches. If these converters operated using the same DC supply and duty cycles, we can see the buck converter has better performance than the buck boost converter in producing the minimum output voltage values. Similarly, the boost converter shows better performance in producing the maximum output voltage than the buck boost converter. Nonetheless, the margin of the minimum and maximum output voltages are considered small. Thus, this issue can be neglected. In the next video, we will discuss how to derive these voltage equations.